Hello everyone, I am Jati from Temasek Labs, NTU Singapore, and today I will present our work on Zynq-7000 SoC, and that's breaking RSA authentication and decrypted Bitstream recovery from Zynq-7000 devices. So the work is done by me and my colleagues Prasanna and Shivam Basin, and yeah, let's start. So basically, Zynq-7000 is a very widely deployed series of FPGAs from Xilinx, and it has a lot of use cases in defense, aerospace, and medical applications. And what we have done is that we have found some vulnerabilities in the RSA authentication process of this secure boot in Zynq. So this vulnerability is present in FSBL, the first stage bootloader, and which can allow us to run anything, run any code within the FPGA or SoC, and as a result of that we can get root access, and then we can recover bit streams or which are normally encrypted and not available from outside, but we can access them and we can decrypt them as well. So, and after this we also try to do the same thing for the boot ROM, and I will show what were the results. So let's so basically there will be some background so that you can understand what's going on, and it will be on the all basics of things that we used. So let's start with the attack model. So we assume that the attacker has access to the device. It means physical access. So without physical access it will not work, and somehow, because most of the bitstream images are in the external memory, like SD cards or external memory chips, so it's assumed that the attacker has access to that as well. So he has a copy of it from the SD card or other places. So boot image access is there, and the RSA is enabled, because obviously we're trying to attack RSA, so it must be enabled. So that's that. And other than that, we don't have any other requirements, and the attack works both for eFuse and battery back time. So either of them can be used and the attack still works. And yeah, that's it for the attack model. So I'll first then go to the boot structure of the boot image. So the structure of the boot image is that basically it's a big file and it has multiple segments. So I'm not going into much detail, but it has multiple parts. So one is the boot header that we call BIH, boot ROM header. So it gives basic information, and then we have a PST partition header table, first stage bootloader, and then the PL partitions for the bit streams, if there can be multiple ones, and they can be loaded based on the user's choices. And we also have applications which run on the FPGA, so there can be multiple cores, and so it can have multiple applications running on them. And the OS, if for example Linux or other things are running, it will be also on a separate partition. So, and all of these partitions can be encrypted, authenticated using HMAC or RSA. But for our case, we are assuming that RSA authentication is used, because the other cases are actually they are kind of broken. So Xilinx actually acknowledged that they are broken in some ways. There are techniques, but we show that even the RSA is broken. So yeah. So as you can see in the boot image structure, the first two parts are not encrypted. So the boot image header and the partition header table is not encrypted, and the lower three ones, the encrypted parts, are the first stage bootloader, PL, and PS. These three things are actually encrypted, and we work to decrypt them through this attack. Now I'll go into some more detail. Is that there are certificates attached to each of those individual elements which needs to be protected, because it's RSA, so they are signed basically. And you can see that there are in this example, for example, there are 4 different certificates which are used. So, but the most important thing is the partition header table, because it contains information that which part of the image is actually protected, which is not. So for example, if we can attack the partition header table, we can change anything. So basically the chip will not know which part is secured, which part is not secured, and it will enable us to run our code on the chip. So there are some more details. One of that is that the signature scheme that we use is RSA 2048, and there are 4 different keys, like the primary PPK, primary public key PPK, primary secret key, and the secondary primary and secret key. So there is this hierarchy is there, but the thing is why this is required. So the main requirement is that only one of them is protected. That's the primary. The primary keys are protected because on the eFuse, which is the one-time programmable memory, normally the hash of the PPK is stored. So basically the initial boot ROM validates that okay, this primary key is genuine and I should use it just by knowing that the hash is correct, so that it knows this key is to be used. And the primary key is used to authenticate the secondary ones, and the secondary ones are used to actually sign the images. So it goes like that. Now, as you can see, the first part, like the boot ROM, boot image header, it contains the encryption status, size of boot image, location and load address and those kind of things, and it is read by the boot ROM. So it does not need to be protected because it does not store have any critical information. Any of that information, even if you change, it will just be a denial of service. It will not lead to any major attack. So yeah, but it contains important information. But the thing is that the next part, the partition header table, it contains information which can be used to perform attacks, and as a result it is signed by the certificate. And yeah, so the whole idea is that if we attack the partition header table in some way, we can basically run anything on the chip and do the attack and those kind of things. And the partition header table is actually read by the FSBL, the first stage bootloader. And our work here is to somehow make the first stage bootloader read a incorrect partition header table. So we want to change the partition header table in the boot image in such a way that incorrect information is read and incorrect information is interpreted and processed, so we can do whatever we want with the chip. So FSBL, the steps is that FSBL gathers information about the individual partitions from the partition header table, and they are loaded into a memory like DDR in this case, and then it is used to step by step load all the individual parts and segments to the RAM and then execute them. Now it starts with first the partition header table first gets information from the boot image and copies it to DDR RAM, and it executes it, and then it, if required, authenticates individual RSA signature parts. So I'm just telling you the FSBL, what does FSBL does. So then it runs the individual PL partitions step by step in sequence, and it goes on for each and every part. There can be multiple segments or there can be a single one, but it does this. But the interesting thing to note is that all the data goes for decryption to the PL and not the PS. PS is the main Zynq part, the microcontroller part, and PL is the fabric, but the AES hardware is there. So there is a PCAP interface, and that interface is used to send and receive data from those. So for all the data that needs to be decrypted is decrypted by the PL. So it has to go through PCAP again and again. So yeah, it goes and comes back and goes to the DRAM. It's also interesting to note that all the data is already in the DRAM. So if there is some DRAM attacks or data from DRAM can be read, then none of this is secured anyway. But obviously it's quite difficult to read from DRAM, normal devices, so it's okay. Now, what we did is we found a vulnerability in the way it reads and processes these things. So I'll go with I'll show what we found. So now, when the FSBL starts working, and this is the most critical part, is that it first queries the partition header table, which is the main thing which you want to attack from non-volatile memory, that can be SD card or other things. So it queries it from the SD card and receives one copy of PST. So we are marking it PST1. Now it checks if RSA is enabled or not. If it is enabled, then it again queries for PST and certificate from the SD card, and it receives the second copy of the partition header table, and the certificate. Now, instead of using the original one, it uses the second one. So but in processing, it uses the first one. So I'll explain again that it queries for PST1 and it does not authenticate it. It copies this, it asks for it the second time and it does authenticate it. So now because and the thing is that you are using the first one, which is not authenticated. So it's a very silly mistake from their side, I will say, but they have done it, and it's in all devices till 2020. So like 8 years of devices, every board that is deployed worldwide has this vulnerability. Any FPGA that you see will have this issue. That so unless you upgrade it, anybody can read your code even with RSA or encryption. So now what happens is that but this is just what we found just by reading the source code, and it's there on GitHub, so you can read as well. So but the thing is, once we found out, we had to use it, because to use it's not that simple. So what we did is that we thought of a way that okay, we can have a device where the input SD cards can be switched or read. So basically, when it boots up, we'll provide one SD card with a tampered image, and it can switch to the other one to verify the correct one, and then it will continue booting. So this is what we did. That we used a multiplexer chip and to switch these two devices, and once this switching thing works properly, then the attack actually works. So so I'll now explain how the SD card switcher and that thing works. So you can see this is the PCB I designed. So there is a U1, that's a small chip. So it's just an analog switch. So using this switch, we can switch between two SD cards. So there is one wire below, like this GPIO trigger, using which, so basically your attack image can be in SD card 1 and the normal image can be in SD card 2. So when those things are there, so just by changing one pin, we can switch between SD cards. So the FPGA does not know. So obviously I'll go into much detail how it works, but the basic idea is that we can switch SD cards. So because the firmware is reading twice and authenticating only once, will once give it the wrong information and then give it the correct information. So it happily authenticates, but it actually is running the incorrect one. So that's the attack. So you can see this is the photo for the device. The pink one is the pink board, and the purple one is the board I designed, and there are two SD cards on it, and it's connected by the green one is just for power supply, nothing, there is nothing else, it's just the power supply. And so this is just the basic one. And so what happens is that on the SD card one on the left side, we tamper the SD card image to whatever image we want, and on the right side on the SD card 2, it's the original one, untampered. So when the time comes, we just have to switch SD card to SD card. So normally it boots from SD card 2, and in the critical time we switch to SD card 1 and again switch back. So the FPGA does not know anything, and then it happily runs whatever code we want. So so that's the thing that we initialize so there is one critical thing to note, that there are two SD cards, but to do it, the initialization is sent only once. So for the attack example that we did, we changed the FSBL in a way that we provided the initialization to the SD card again, but technically it can be done externally as well. But just for the demo, we just, because it's just a simple SDIO initialization commands, few commands need to be sent to make the SD card ready for commands. So now this is just the flow. It's showing that we are sending queries from PSD from SD1, and it receives tampered PST, and then it checks, and then again it sends the request to SD card 2, and then gets the valid and authenticates it, but use PST1. So it goes like that. And as I mentioned, the second call to SD is not there, so we insert it in the image. And as a result of all of this, what we talked to Xilinx, and they confirmed that it's an issue, and they published a CV, and so basically the attack works. So they did a major patch to the source code, and they kind of fixed it, because now they are using only one array. So they are using an internal array to store the temporary results, and then executing as required. So the attack no longer works with the updated ones, but all of the chips that are made, or all of the devices which are made, like oscilloscopes and other things, or many other things that are made, so all of them can be attacked, and you can recover the bit streams, you can recover the source code for the application, like compiled obviously, but it can be recovered from fully encrypted ones. So yeah, so now the thing is that I just showed you the attack technique using which you can break RSA, but we have to also recover the things, like, because breaking RSA is not enough, you have to recover the data segments chunk by chunk, and there is no way to access outside, because many devices, what can happen is that they can disable the JTAG, so there is no JTAG access, so it's fully black box. So now what do you do? So to do that, we tried many things, but by running many commands, modifying the image to run some commands to enable JTAG, but none of them worked. So once it is enabled, it stays enabled. But then recently a work by Mike Ender et al., and what they did was they did recovery of bit streams, byte by byte recovery of bit streams on Zynq-7000, not Zynq, the normal Xilinx 7 series, like the Kintex or the RTX series of FPGAs. So on those devices, they could attack it. So we used that attack, and that attack is called Starbleed. And what it does is that there is a register called WB star, and that's called the warm boot startup register. So what happens is that sometimes if there can be a situation when you want that, okay, the FPGA is booted up, but it failed to do something. Then you store some registers that from where it should boot next, and then reboot the FPGA. So temporarily that information is stored in the WB star, because the WB star, when the chip resets, goes through power cycle, the WB star data is not deleted. All other registers are deleted, but this is not. And what they did in their attack is that they modified the bitstream in a way that the important information is being written to the WB star. So that's a different attack, but we use that technique to do that. We can make small bit streams, use our RSA attack, and combine the two techniques to generate basically an application, to basically not generate, but write an application which will run this in a loop and then do the attacks. So let's go how it basically works. So in WB star attack, like the Starbleed attack, first uses a bit stream which is tampered, and it writes the information to the FPGA. So once it is written, WB star is updated with a small segment of code, and that small segment can be anything. So I'll show later how that segments are created, but I'm just giving the basic idea here that a bit stream can be like 1 megabyte long or few megabytes long, but this attack bit stream is very small. It's like few kilobytes and few bytes, like less than a kilobyte long, and it just tells the FPGA to copy a decrypted word to a certain location, and that's WB star. Obviously it's all hex code, so I cannot explain that much, but I'll show it. I wrote a tool which shows what to do. Now once this thing works out and the decrypted word is available, step by step you can read all of the encrypted bytes, and the whole bit stream can be reconstructed. But the same thing does not work on this Zynq-7000 directly. What we had to do is that we tried many things, but after many attempts, we finally could succeed to do this, because see, the inner architecture is similar. Even the Zynq part is an addition to the PL part. The PL part more or less remains very same, so all the commands actually work there as well. So how the attack works is that we have a malicious boot image, and it runs on PS, and then it sends a command. Basically it starts working because initial part is correct. So initial part is correct, and then this PCAP, so a small bit stream is sent over this PCAP. So I'll go back a bit. So this part assumes that the previous part is actually working, RSA is working, and using the RSA we are actually sending this attack bit streams. So is it clear that the first technique that I explained, RSA, that is used to do this second part, and the second part is sending small bit streams to the FPGA and getting part by part. But here what happens is that working start bleed attack on a, what do you say, so main challenge here was the development of attack to carry out the start bleed over the PCAP interface. So this PCAP interface is new on our RSA. So because this PCAP interface is not on the normal 7 series FPGAs, we had to do a lot of things, and which included making this tool, which I told earlier. So this tool allows you to put a bin file and a key file, which you know already, just to study. So using this, you can add faults. Faults means single bit faults. So I can have a list of fault items where I can set a value. Okay, byte number 76 is being written with some XYZ value. So that value will be XORed with the input. And using that, this on the top right side, you can see the TIWWB star 38. That means the next 38 bytes of the image or the encrypted part is to be consumed by the WB star command. So it's a bit more technical, the paper has much more information, but basic idea is that the WB star, it works like this 26 hex means 38, and that many words are to be consumed by the FPGA engine, and the last one will be stored in WB star register. So that's the basic idea. So using this technique, we can introduce faults to an actual correct bit stream and then generate this attack bit stream which is consistent with all the rules. So in this case, we had to do two faults, and using the two faults, we are able to create a bit stream which actually is loaded by the Xilinx FPGA and it works correctly. So, and rest of the things are not required. So it becomes a few kilobytes. So the thing that you are seeing here is the only part that is actually required. So that before and after we just remove. And the important part is that you can see this in this command, the last line. So last line is like 48D1 E1 AC. So this value will be actually be found in the WB star register when you read over JTAG. And now if this line is changed, like the line 440, if the whole line 440 is changed by an unknown item, so that will be decrypted and be made available on the WB star. So is it clear? It's a bit complicated to explain, but the thing is that what you are seeing is a decrypted bit stream. In actuality, it will be an encrypted one, but the tool is showing you what will happen if it is decrypted, how the FPGA sees it. So this part is actually decrypted, but the encrypted part you can copy from all of the image. So image is very large. You can copy this 4 words at a time, and then replace this 408 line. You can replace 4 words at a time, and the last chunk will be used to the last four bytes will be decoded one at a time. So you have to run it continuously over iteratively, and after a long time you will see that everything is decrypted. I'll show the tool at the end so that you can see. So now the thing is how this thing is created. So I'll just go into some basics. The basic part is that on the left side we take a boot image header, and we manipulate the partition header table as I explained earlier, and then we can have lots of multiple bit streams. We can have like hundreds of them, and then when the application runs and because the attack application is also in our control, so that attack application can run one after the other bit streams, and after all of them are run, after running every time, it can just store, send over UART so that you can copy and store the data. So this part is done, and just as I explained, we use the Xilinx SDK to develop this application, and it works with the whole setup. And so there are some experimental observations that when initially it worked with secure boot, in the first attempt it works well. It means, but the thing is, we know that there is an HMAC error, because as I showed you, this part of the image that you are seeing the top left, the line from line 184 on the left side, that whole chunk, like a whole block on the lower side, that is the HMAC, the keys and HMAC parts. And similarly, a block like that is available at the end. So there are 3 such blocks of code which contains the HMAC keys. And because let's say you are not attacking the HMAC part, you are not using the HMAC part, so the HMAC test will fail. So even though the command for WB star has executed properly and we are able to recover the WB star, but the next operation will not work because this HMAC is not handled. So basically we'll get an HMAC error and then we have to reboot. Reboot means power cycle, and power cycle with the next value. So that, but if you keep on doing it like that, you can power cycle as much as you want, doesn't matter. So we ran the device with power cycle for many hours and it ran perfectly fine. So yeah, but before that, also the thing is that this WB star reading principle that we are using JTAG for this, because as I told, from JTAG you can access it, and but in reality this JTAG is not available for the actual attacks. In some cases the JTAG may be disabled. So in that case, after the first attack it actually does not work, because I'll explain why. Because when the code is the bitstream, when you push the bitstream, the first attack bitstream, when the HMAC error happens, the whole device freezes and you cannot access anything. But the way to do it is that first you write a correct bitstream, which will not fail the HMAC tests. And if it does not fail the HMAC tests, you can see the done signal of the FPGA goes high. And once the done signal in the FPGA goes high, then the next other bit streams that are executed, they will be the next bit stream that is run after the done, it will not cause the HMAC error. So that's the critical part, and it's actually, it took several months, like 5-6 months to understand this, that even if everything is correct, it will not work. First you have to make the done signal high, and then after the done is high, you can put a bad bit stream, and it will execute for only once, and then you have to restart. So this is the critical part of the attack, and once it is done, the WB star will update with the actual value that you want, and then word by word we can recover the complete image. But yeah, as I said, that after it happens, it goes through a power cycle. So our attack setup uses this kind of a strategy, that there is Arduino based tool and there is a PC, and we have small software which runs to reboot this again and again, and yeah, we get 4 bytes at a time, and yeah, the whole thing works. So on the current setup that we have, it's not very optimized, but we can get 4 bytes in 1 second. So we can get, in 46 days we can get 3.85 MB. It's quite slow, but yeah, if you have 10 such devices, you can make it faster. Yeah, but yeah, so it's. But the thing is that we have not tested with the HMAC part. Let's say we try the HMAC verification. It may not, the HMAC which is failing and causing the device to freeze, it may not happen. And in that case, it can be made faster. But anyway, all of this was not required because Xilinx fixed the attack and then we stopped work. So, but it can be made faster. Yeah, so. Yeah, so so this is the, I think I explained this part. So I'll just show a small video. So this is, yeah. So as you can see, this is the pink FPGA device, and this is the original unencrypted bitstream. So unmodified. So when you run the unmodified one, you can just put the SD card and it will boot up. So when you can see the terminal, that at the end you can see that it's executed. I am victim, I am working correctly, because it's just an example. So it prints that okay, it ran correctly. So now we are changing the image, to do the tampering. So this tampering will cause the signature to fail, because signature we did not change, we just changed the application. So this is in the second SD card. So second SD card just changed the tampered image, and it is not authenticated. Like it is authenticated, but it will fail because the key is wrong in this case. And you can see when it runs after. So we just add some prints so to make it slow. Yeah, you can see the signal. I'll just what happened? Sorry. It's not working. Should I run the video separately? It's not working. Can I run the video separately? Let's just. Yeah, so on this one, so this one I showed you, and so this is the second one, and this one you can see the authentication has failed. Partition header table authentication failed. So this is for the second one, and after it runs, we try the next one. So you can see the partition SPK authentication failed for the second one. And now what we'll do is we'll use the SD card switcher. So using this switcher, we'll have two SD cards together, and we'll have so this SD card switcher is shaped in the shape of SD card, so you can just connect it. So once it boots, so I think the camera will, yeah. So here you can see it is running, and so basically we have had a small pause, but that pause is not required later. So you can see it actually ran the wrong image, and it says successful handoff. So what this means is that after that 2-second pause, if you switch the SD cards, it actually boots the wrong image, which failed just earlier because of authentication. So that's that. So wait. Yeah. So there are some more things after this, and that is so this is the attack, and there are some more things. The more things is that we wanted to make sure that this vulnerability can be patched by Xilinx, but now we want to see what we can do if, let's say, this vulnerability is present in the boot ROM as well, because boot ROM is physical silicon, it cannot be tampered with. So this part they can say, okay, download the new patch and install it and it will work fine. But we wanted to see if it is in the boot ROM as well, which cannot be changed. So now we have the last part of the talk. We'll just show some analysis. So I'll go quickly. Is that okay? So I'm just giving an example using the SD card interface. So SD card interface has mainly two wires, CMD and clock, and 4 data lines, and we are interested in the CMD commands. Now there are two important commands: the single block transfer, CMD-17, and CMD-18 for multi-block transfer. And the most critical part is CMD-17 because it is used by the boot ROM. It does not for some reason use CMD-18. And yeah, so basically we're monitoring for CMD-17 and 18 calls, and once it happens, we'll basically see how it goes step by step. So we used a logic analyzer to analyze the individual parts, and you can see a small logic analyzer connected to the board, and we are just getting the data. So yeah, so basic idea is that the boot ROM runs, it copies the information from the FSBL, this boot image here, and it runs goes through the process. And earlier we ignored what happens, but now we'll focus on this specific part, what happens. So now you can see this is the full boot up run. So CMD and clock. So you can see on the left side there is some data transfer over the CMD, and after that there is a large data transfer, and then it stops with a small data transfer. But what do these things mean? We don't know. So in order to understand what happens is that we inserted a delay to the FSBL code, like just 10-second delay, just to get the information what it happens. And after the analysis we found out that this first part is the retrieval of the FSBL, like the first part. The second part is the init commands. Then we are retrieving the FSBL, and then we have the last part is the software application. The software is the ELF file that is running on the, let's say, microblaze or the actual chip, like the Zynq, ARM Cortex. So SW is the application for the ARM Cortex. So anyway, so these are the 4 things that we can see on the logic analyzer, and we are also able to see this read command, read multiple blocks. So these kind of commands and responses are used for the during the retrieval of the first stage bootloader. But okay, we understood it much, but we're not interested in this. We're interested in what the boot ROM does. So if you see, so okay, before that we can also show that the boot after the initialization happens, the partition header table is read. I told you that we have 2 reads, so we can actually show that it is read once and again read. The same addresses goes twice. So we can see that the same address being read twice in the data stream. So because of this, we can also verify it happens twice. But you can see that there is a delay of 3 milliseconds. So in the example, what we use a switch to switch the delay manually, but technically there is only 3 milliseconds time. In that time frame, we have to switch. So basically, we need FPGA to monitor the communications and switch at the critical time. So that critical time is 3 milliseconds. So it's very large for such devices. And if you are able to switch between these 2 PST1 and PS2 accesses, then the attack will work. So these timings are quite important. Yeah, because the attack has to happen between the PST1 and PST2. The switchover. And the switchover and the board that I designed, the switchover can happen in a few nanoseconds. So that's not an issue. The SD cards are quite fast to switch. So now we go to the boot ROM analysis, and there are 3 use cases. That's non-secure boot, and secure with encryption, and secure with encryption and authentication. So all 3 of this requires different amounts of blocks of data. So one is 114 kilobytes, 225 blocks, and you can see this is the basically trace of that, the boot ROM execution for unencrypted one. And after the yellow line, vertical line, you have the FSBL execution. And then we have this is with encrypted bit blocks. So basically it matches the calculations. How many bytes are required, the chip actually reads exactly that amount. And then this is 230 blocks are for the encrypted one. So this also matches the expected reads. So we can see show conclusively that it does not read any bytes extra. So whatever is required, it reads only once. So the attack which worked on the first stage bootloader, it does not work on the boot ROM. So yeah, it's good from Xilinx side that it is safe. Yeah. So to conclude, I'll show that we have a critical flaw in the Zynq-7000 FSBL, and yeah, due to the mishandling of the PST data, and we have validated this, and there is a patch, and yeah. So, but the most critical part of it is all the deployed devices which are unpatched remain targeted, and yeah, if anybody can attack them. And yeah, so we also show the first vulnerability analysis of boot ROM and show that it is actually secure. Yeah. So in the future, we plan to see if there are some more attacks possible, and also the fault analysis. So we're quite interested. So we're trying injecting faults to this, but we have not done yet. Yeah. So these are the future works possible. Thanks a lot. So any questions?
Hello. Hey, thanks. I was just wondering about the SD card switchboard. I mean, obviously it's the right solution for this case, but have you considered something like modifying an SD card firmware or even emulating an SD card? Just thinking about it might be more flexible in particular when it comes to like tight timings.
Yes. So so basically the thing is that we tried to do that on an FPGA. We tried to make a fake SD card, but there are so many commands, so many work, because the most open source SD card things, they are like there is one master and slave. So the master part is available to control SD cards, but what is inside the SD card, we could not find any repositories which we can easily copy. So that has to be written.
It's a pain.
Yeah.
Okay.
Yeah. So that part we could. So we did not do this. We did this one.
Unfortunately, I thought I could steal something, maybe.
Yeah. Yeah.
Does AMD have a way to deal with revocation of the FSBL? Is there a way on an existing chip, which already shipped, to block loading an older FSBL version?
So see, if a chip is deployed, I don't know of any such ways that they can remotely do. Because if, let's say, they can remotely do, it becomes a different target for like denial of service. So let's say there is a device available. If you have a way to stop something or change something, it becomes difficult. So I'm not aware of any such ways to like change that part.
Okay, so in the documentation, they don't talk about revocation.
So once deployed, there is no revocation, right? So once you deploy it, the device is on the field, it's running. There is no internet access to it, and there is no way it can change its own image. Unless you update the image, there is no way it will automatically update itself. So a developer can introduce it. Like if a developer wants, they can introduce such things to their own code. The FSBL can be custom.
Thank you.
Yeah, thank you.
Thank you.